This presentation is a continuation of the case history of the 2011 Mississippi River flood at Chute Levee. The first part of the case history examined the flood event and evaluated the factors that made backward erosion piping more likely and less likely to occur. This portion of the case history will examine the intervention activities that were performed at Chute and evaluate their effectiveness at the prevention of levee breach due to BEP. During the presentation, we will identify the key factors that were important in reducing the likelihood of failure of the levee and apply those same factors as indicators to guide judgment when assigning more and less likely factors and assessing the likelihood of unsuccessful intervention occurring at another structure. The first portion of the presentation will summarize past performance issues that have been observed at Chute, followed by a summary of the BEP factors discussed during the previous case history presentation. A summary of the specific flood fighting efforts performed at Chute during the 2011 event will follow, along with an evaluation of their effectiveness. And finally, the more and less likely factors for BEP will be examined one more time, this time with intervention included to see how the balance of factors is affected. First, a quick reintroduction of the project area and a summary of past performance at the levee. Chute is located along the main stem levee system of the Mississippi River and Tributaries Project, 16 miles northwest of Vicksburg, Mississippi. The mainline levee was constructed between Eagle Pass and Eagle Lake, two channel deposits associated with the Mississippi River. As stated in the first case history presentation, Chute is considered one of the weakest areas along the MR&T due to poor performance during previous flood events. Two potential backward erosion piping locations were examined in the first presentation, the northern area and the southern area. A more in-depth discussion of past performance issues in these areas is needed to provide context into the thought processes that led to the 2011 flood fighting efforts. In the northern area, the history of poor performance was less tied to the amount of observed performance issues and was instead more significantly focused on the severity of the single issue that was encountered. This section of levee had experienced a differential head load greater than 20 feet several times prior without any indications of seepage or sand boils landside of the levee toe before 2008. In 2008, the river elevation crested at approximately 107 feet, while the elevation of Eagle Lake was 77.64 feet, resulting in a differential flood load of 29 feet. This was the new highest load to date experienced by the embankment, although it should be noted that very little records exist for prior historical floods. At the time of the 2008 event, no performance problems were observed in the area. In February of 2010, a local landowner discovered several voids on the land side of the levee that were observed to be as much as 20 feet wide and 10 feet deep. Although no performance problems were observed at the time of the flood, Vicksburg District personnel believe that these voids may have formed unobserved during the 2008 event. Later in 2010, the levee was exposed to a flood load of approximately 21 feet, which is 8 feet less than the 2008 event and less differential loading than had been experienced several times prior to 1997 and 2005. During this event, levee operations personnel observed more boils and voids on the land side of the embankment in a heavily wooded area. The progression of poor performance at lower differential head indicates that an erosional process had likely been initiated. Poor performance in the southern area dates back to the flood event in 1997 when the levee experienced a flood load of approximately 26 feet. During this event, sand boils and heavy seepage were observed on the land side of the levee. This prompted the installation of 6 6-inch diameter relief wells in the vicinity of the boils to reduce foundation seepage pressures. In 2005, with a flood load of approximately 23 feet, several pin boils, by definition less than an inch in diameter, were observed in the relief well field. In response, the Vicksburg District installed an additional 3 14-inch diameter relief wells to further relieve foundation pressures. During the 2008 flood event, no performance problems were observed at the relief wells, but sand boils were observed approximately 1,300 feet land side of the levee at the shore of Eagle Lake. Finally, in 2010, with a flood load of 21 feet, no performance problems were observed near the well field or near Eagle Lake. So contrary to the northern area, which saw performance degradation with time, the relief wells in the southern area seem to have provided adequate seepage pressure reduction to prevent poor performance in the immediate vicinity. The remainder of the presentation will focus on the flood fighting efforts performed during the 2011 Mississippi River flood and their effectiveness to prevent backward erosion piping. At Buck Chute, the river reached elevation 112.9 feet, which exceeded the previous high water level observed during the 1927 flood. With Eagle Lake at its normal level of approximately 78 feet, this resulted in a differential flood loading of 34.9 feet, greater than any flood load experienced by the embankment. Following the discovery of the extensive sand boils and voids in 2010, a fast-tracked geotechnical investigation and design effort for construction of seepage mitigation measures at the levee was initiated. In March 2011, before the permanent measure could be designed and built, the Mississippi rose to 98.95 feet, which resulted in a differential loading of 21 feet, which was comparable to what was experienced in 2010. At this point, the boils discovered in 2010 were reactivated and sediment was observed to be flowing out of them. With the river projected to rise to a level that would produce an additional 15 feet of flood load, the decision was made to implement emergency measures to combat foundation seepage. In the northern area, the decision was made to construct an emergency berm on the land side of the levee to increase the weight of the landside soil block. The berm consisted of a perimeter clay dike with the interior filled with a minimum of 3 feet of clean sand capped with 2 feet of clay. The exterior of the berm was covered with a 10-foot wide and 2-foot thick layer of stone, with the toe of the berm having an elevation of 85 feet, 5 feet above the original ground surface. Another major intervention action undertaken was a manipulation of the water level of Eagle Lake. Eagle Lake was formed back in the 1860s when it was cut off from the main Mississippi River channel. Throughout its history, it has been an unregulated lake with the water surface elevation rising and falling during flood events due to backwater flooding from the Yazoo River. Prior to 1973, the fluctuating lake elevation allowed for water to inundate the Buck Chute Levee landside toe during high water events, effectively reducing the head differential experienced by the embankment. Around 1973, the Muddy Bayou control structure was constructed as a fish and wildlife mitigation feature for the Yazoo Basin project to prevent agricultural runoff from the neighboring Steel Bayou from entering Eagle Lake. After construction of the control structure, the elevation of Eagle Lake became regulated with a dedicated water control plan that keeps the elevation relatively constant. This resulted in two consequences. The first is that the lack of elevation rise in the lake prevents the inundation of the Buck Chute landside toe, increasing the differential head experienced by the levee during flood events. The second consequence is that since flooding of the lake is no longer a regular occurrence, residential and commercial development centered around recreation has occurred along the lake shoreline. With the Mississippi River elevation continuing to rise and the levee embankment and untested emergency berm being subjected to record flood loading, engineers with the Vicksburg district didn't feel confident that the emergency berm alone would be sufficient to address the developing seepage and boil issues. Geotechnical engineers advised that a combination of berm and landside water load would be necessary to adequately fight the underseepage forces that would be present during the flood. After serious considerations of the pros and cons, the decision was made to deviate from the water control plan for the Muddy Bayou control structure and raise the elevation of Eagle Lake to 90 feet, 12 feet higher than normal. This decision resulted in the impact of approximately 800 residents around Eagle Lake whose property became flooded. However, this was a measure against the possible inundation of approximately 3,000 homes and 1,450 square miles of largely agricultural land if the levee embankment were to fail. The question now turns to this: just how integral were the efforts at Buckshute at preventing failure? Re-examining the backward erosion piping evaluation from Part 1 of this case history can provide insight. As a reminder, here's the typical event tree for backward erosion piping. The flood fighting efforts primarily affected the initiation and hydraulic condition for progression nodes within the tree. Typically, intervention is accounted for in the risk estimate through the unsuccessful intervention node. However, since this case history is an examination of events that occurred in the past, it's prudent to look at these nodes separately. First, we'll evaluate how the emergency efforts affected the likelihood of initiation of backward erosion piping. Prior to the flood event, the Vicksburg district performed an underseepage analysis to determine the expected factor of safety against heave based on the forecasted flood elevation and different landside water elevations to account for the ability to raise the elevation of Eagle Lake. In the northern area, these calculations did not include the construction of an emergency berm, but were evaluated to determine whether the risk due to backward erosion piping could be sufficiently reduced without additional flood fighting measures. The factor of safety against heave with Eagle Lake at its normal water level was 0.72, with a calculated gradient of 1.1 well above the critical gradient of 0.8. This was an expected result, and it aligned with the observed poor performance during past flood events. Factors of safety with Eagle Lake elevations of 90 feet and 93 feet were both calculated to be greater than 1.0. However, it was noted that achieving a lake elevation of 93 feet was more desirable, as the factor of safety with a lake elevation of 90 feet was only 1.03. In May 2011, it became apparent that the water elevation in Steel Bayou, and thus the maximum water elevation that would be achievable in Eagle Lake, would be no greater than elevation 90. It was therefore concluded that a raise of the Eagle Lake water surface alone would be questionably sufficient to resist seepage pressures. Based on the results of the analysis, it was determined that the construction of the emergency berm was also necessary, but the analysis was not expanded to include the berm in the calculations. A blanket theory analysis was performed by the Risk Management Center after the 2011 event to gauge the effectiveness of the flood fighting efforts to prevent heave. This analysis included a probabilistic first-order second moment analysis to determine the factor of safety against heave and obtain a probability of heave for 3 different configurations of flood loading and mitigation measures. The Mississippi River was originally forecasted to crest at an elevation of 108 feet. The first case that was analyzed used this flood elevation and did not account for any landside flood fighting efforts. The flood differential was 28 feet, roughly equal to the flood differential experienced during the 2008 event. The calculated probability of heave from this case was 99.7%. This aligns with the formation of the boils and large voids that were suspected to have formed during the 2008 event. The second case adjusted the flood elevation to reflect the actual Mississippi stage of 112.9 feet, and it accounted only for the presence of the emergency berm on the land side of the levee. This scenario had a flood differential of approximately 33 feet, which would have been by far the largest loading experienced by the embankment. The resulting probability of heave for this case was 99.9%. The final case evaluated the actual conditions present during the flood, with a flood elevation of 112.9 feet, the emergency berm on the land side of the embankment, and Eagle Lake at elevation 90 feet. The flood differential for the final scenario was approximately 23 feet and had a probability of heave of 21.8%. Based on this analysis, the combination of the emergency berm and the Eagle Lake raise produced a significant reduction in the probability of initiation of backward erosion piping in the northern area. A similar pre-flood analysis to determine the factor of safety against heave was performed by the Vicksburg district in the southern area. The ground surface in the southern area is slightly higher in elevation than in the northern area at 84 feet. Without raising Eagle Lake, the calculated seepage gradient of 1.08 results in a factor of safety against heave of 0.75, which is very similar to the results in the northern area. With the elevation of Eagle Lake raised to 90 feet, the seepage gradient begins to approach the critical gradient with a factor of safety of 0.91. With Eagle Lake at an elevation of 93 feet, the factor of safety is only slightly greater than 1 at 1.05. With the presence of the relief wells and the lack of recent poor performance in the southern area, an emergency berm wasn't warranted to reduce foundation pressures, and the maximum possible elevation of Eagle Lake of 90 feet was not sufficient to produce a factor of safety greater than 1. However, the increased lake elevation successfully reduced the expected foundation seepage gradient to near the critical gradient, and it's likely that the probability of backward erosion piping initiation was decreased. The other node in the backward erosion piping event tree affected by the flood fighting efforts is the hydraulic condition for progression. Recall from the first case history presentation that the northern and southern areas contain differing seepage exit conditions. The northern area exhibits a hole type exit through defects in the confining layer, while the southern area contains an area type exit. The hole type exit in the northern area results in a focus of underseepage and a reduction in the critical gradient for progression of backward erosion piping by a factor of approximately 2. Absent any flood fighting efforts, the average foundation gradient in the northern area is 0.047, which is approaching the critical gradient of 0.051 based on the adjusted Schmertmann method. In the southern area, the average foundation gradient of 0.041 is well below the critical gradient of 0.101, again based on the adjusted Schmertmann method. The presence of the emergency berm in the northern area pushed the exit location for seepage 100 feet beyond the area of the boils observed in 2010. In the existing condition, the probability of progression was approximately 40% based on the probabilistic approach for evaluating the likelihood of backward erosion piping progression in the RMC Backward Erosion Piping Progression Toolbox. Once the berm was constructed, the seepage path length from entrance to exit was lengthened from 700 feet to 800 feet. It's assumed for this case history that additional defects in the confining layer exist beyond the landside berm toe that result in a similar hole type exit and critical gradient reduction as the location of the 2010 boils. With the berm alone, the average foundation gradient is reduced to 0.041 with a probability of progression of approximately 25%. When the berm is paired with the Eagle Lake raise, the average foundation gradient is reduced to 0.029, well below the critical gradient for progression. This carries a corresponding probability of progression near 7%. The combination of the two flood fighting actions produced a significant reduction in the likelihood of backward erosion piping progression in the northern area. When evaluating the southern area, it's shown that the average foundation gradient of 0.041 is already well below the critical gradient of 0.101. The raising of Eagle Lake reduced the foundation gradient even further to 0.033. However, the probability of progression of backward erosion piping in the southern area was already very near or at 0%. Therefore, the flood fighting efforts didn't provide a great benefit in the southern area for this node. After evaluating the effectiveness of flood fighting efforts at Buckchute for the initiation and hydraulic condition for progression nodes, the more and less likely factors for backward erosion piping can be re-examined to see how the balance of factors was influenced. In the northern area, the flood fighting efforts result in two new, less likely factors related to initiation and progression of BEP. The emergency berm and increased elevation of Eagle Lake reduced uplift and the differential hydraulic head experienced by the embankment, and also reduced the average gradient in the foundation by extending the seepage path. The likelihood of initiation has changed from a near certainty to unlikely, and the likelihood of progression has changed from neutral to between unlikely and very unlikely. Additionally, the original more likely factor related to the hydraulic condition for progression of BEP has been eliminated. Overall, it can be reasonably concluded that the intervention efforts dramatically reduced the likelihood and likely prevented major damage of the embankment or breach from backward erosion piping in the northern area. In the southern area, the flood fighting efforts bolster two of the existing less likely factors related to BEP. The increased elevation of Eagle Lake increased the factor of safety against heave at the seepage exit location and reduced the average gradient in the foundation further below the critical horizontal gradient for progression of BEP. While perhaps less effective than in the northern area, the intervention efforts undertaken had an effect on the likelihood of BEP in the southern area. Based on the comparison of these factors with and without considering the flood fighting and intervention efforts undertaken during the 2011 Mississippi River flood, it's likely that near failure or failure of the levee embankment was prevented. This concludes the case history presentation on the intervention efforts undertaken at Chute Levee to prevent backward erosion piping during the 2011 Mississippi River flood.